Good evening, everybody, and welcome to the Chesapeake Biological Laboratory. I see a few familiar faces, so welcome back again. This is the third of 5 lectures that we'll be doing throughout this month. So I see some, oh, nearly got the IT in there. There you go. Okay. So first of all, happy Earth Day, everybody. Yeah. So I'm sure we've already discussed that with a number of people. Today, April 22nd, 2005, Earth Day. And I've just put in a few images here from our wonderful ecosystems throughout the Chesapeake Bay and our wonderful iconic critters as well. So happy Earth Day, everybody. So for those new in the audience, I'll keep this brief also for those that have heard this 100 times. But the Chesapeake Biological Laboratory, we were founded in 1925 by Dr. Reginald Truitt. So for those of you who can do math, yes, it is our 100-year celebration. So really excited to be celebrating that this year. And so throughout this, you'll see some QR codes. Feel free to take a picture. Also the web address is there as well. But we'll have a number of events celebrated across UMCs for this year. So keep an eye out for anything that will be upcoming. So we are the oldest state-supported marine lab on the US East Coast, and we are one of 6 constituent members of the University of Maryland Center for Environmental Science. We have laboratories in Frostburg, we have the Appalachian Laboratory, we have the Horn Point Laboratory on the Eastern Shore, we have IMET, the Institute of Marine Environmental Technology, downtown in Baltimore, we have the Integrative Application Network in Annapolis. We also part Maryland Sea Grant at College Park is part of us, and then CBL. So like, wait, no, I saved the best till last. And so our mission at UMCs is to improve and preserve Maryland's natural resources, some of those nice pictures that I showed you earlier, and address pressing environmental problems. And we achieve this through cutting-edge research to advance scientific knowledge, and most importantly, sharing this knowledge and engaging with policymakers, with managers, and also to the public to try to help provide solutions to fix some of these issues. We are also Maryland's leading university in the education of the next generation of environmental scientists and also working professionals. So why are we all here today for this series? This series is celebrating 100 years of science on Solomons. This is the third, and it was kicked off on April 8th by our UMC's President Emeritus, Dr. Don Bosch, who has written a book all about the history, 100-year history of UMCs. And so there's another QR code and discount code if you'd like to purchase his book. And it's called Predictive Ecology. And again, it talks about the history of UMCs. And so as part of our celebration, we have this public seminar series. You know, as I said, we were established 100 years ago. Dr. Truitt was a true visionary, and he was a real advocate for environmental health. And he established CBL to understand the intricate balance in our ecosystems and combining research on the organisms like the blue crabs and the oysters, but also recognizing that water quality was important drivers for this. So he was pulling all of this together and doing really innovative research for the time. So next week, Dr. Miller, professor here and our previous director for 12 years, he will speak to Truitt's legacy in science. And then the last, concluding our series for this spring, will be on May 6th, and that will be Dave Secor. He will talk about the legacy of Mansuetti. And for those of you who are in the first session, yes, we love to name our buildings by our wonderful scientists here, but also others that are big advocates for environmental science. And so this is my favorite building. This building, the Bernie Fowler Laboratory, honors the late Senator Burley Fowler, who really brought to attention, you know, the health of the Chesapeake Bay and how important it was, and really addressing issues of water quality. And that's what we're going to be speaking to today about, you know, what have we learned with our long-term data set here on water quality. So reflecting on the past 100 years, I've only been here a quarter of that time, by the way, we can recall countless contributions that CBL has made in terms of ecosystem restoration, in terms of fisheries, sustainable fisheries, in terms of biodiversity and addressing water quality, and the impacts of human activity on our ecosystems. So our work has advanced the frontiers of science. Gosh, now I feel like I'm talking about Star Trek, but we've advanced the frontiers of science. And more importantly, we've directly informed policies and managements and practices that help protect and restore the Bay and beyond. A lot of our scientists do work here in the Bay, but we have many, many scientists that are globally in terms of Arctic ecosystems, coral reef ecosystems, all addressing issues relating to environmental concerns. So I have no time to tell you about all of our wonderful scientists who we have here at CBL. They're engaged, like I said, locally and globally on environmental issues. But I did want to highlight Dr. Jackie Grebmeyer, who's going to be really embarrassed because she sat right there. And I mentioned her in the last two talks as well, but this is a nice updated photo. So she recently just went to the award ceremony on April 11th. And this is a really, really high prestigious award. You know, the 75,000 faculty in the University System of Maryland. And this is the University System of Maryland Regents Award for Excellence in Scholarship or Research. And so it's the highest honor they can bestow on a faculty member. And Jackie received it for her and I won't say how long, but for her long-term monitoring and data sets in the Arctic that have been instrumental in determining, you know, climate change impacts and changes in that sensitive system. I also, for those new here, we have a new director at CBL arriving in August, Dr. Beth Polidoro. She joins on August 1st. She's a renowned expert in marine science and environmental chemistry. She joins CBL from Arizona State University, where she's the Deputy Director of the Center for Biodiversity Outcomes, Assistant Director of School of Mathematical and Natural Sciences. So, but what I like to celebrate is our community, our scientists, our students, our staff, and you, our supporters. And so thank you again for being here tonight. We have always been a place of collaboration and community, bringing together scientists, our educators, our policymakers, and the public to engage in our shared responsibility on preserving the environment for future generations. Our environmental issues are complex, and all of us need to be involved in working with them and providing solutions, not just today on Earth Day, but every day. So the building, if you've just driven or walked it, you'll see it doesn't look like this anymore. We've gone a long ways. This is what it's going to look like, but this is our new building. So, you know, I just said we had many environmental challenging problems ahead. We've had them in the past as well. We have climate change, we have habitat loss, we have pollution. These all require innovative solutions, interdisciplinary collaboration, and unwavering resolve. Yet, if the past 100 years are anything to speak to, this laboratory will rise to that occasion. We've had issues in the past, we have issues now. We will fix the environmental problems of now and the future. So we have a new building, this new building on campus, the Chesapeake Analytics Collaborative Building, and it's going to provide state-of-the-art meeting spaces. And I bring up that building because it's part of one of our new initiatives at UMCES, the Chesapeake Global Collaboratory. And the goal of that is to bring all voices together, bring everybody to the table. It's not just scientists, policymakers, it's you, the public as well, to try to develop novel and innovative solutions, tools and approaches to provide actionable solutions to fix these many complicated social and environmental problems that we're facing today. So you will actually hear this thread and need throughout the talk today. So finally, you all know what's coming next. And I've got 14 now, I'd just like to say. So, you know, a lot of our graduate education and small research endeavors are supported by donations to these programs. and many of them only possible through support. So I thank you for, and it's my goal, celebrating our 100 years, I'll get 100 donations. And so that's my goal, to support our graduate students. So in closing, I'd like to express my real deepest gratitude to everybody that has contributed to CBL's success over the years. We certainly couldn't do it without you. So thank you. And I will end and start introducing our speakers. So I would like to introduce Dr. Jeremy Testa, who is an associate professor. His area of expertise is in coastal marine ecology, processes of nutrient cycling, dissolved oxygen dynamics, and ocean acidification. And next, we're doing a tag team tonight, by the way, something different. And I'd also like to recognize Dr. Andrew Hayes, who will be coming up next. He's a research professor here. His area of expertise is in analytical chemistry, trace metal geochemistry, and organic contaminants. And then you don't know about me. My focus is on environmental health and toxicology, and how we detect pollutants in the environment and how we understand their impacts. I'm particularly fond of coral reefs and sensitive and complicated systems. But my research is to look at what's out there, then to design toxicity tests and see if it's toxic and if there's an environmental risk, and provide advice to managers and legislators on what are the priority contaminants that we should be looking at. I can go out and take a water sample right now and get 75,000 contaminants. The question is, what do we focus on and what is important? So with that, I would like to hand it over to Dr. Jeremy Testa. Thank you.
Okay, good. I'm naked without my laser pointer, so I want to make sure I have it. So thank you for that introduction, Carys. I came to CBL in 2013, and at that time, within the first couple of years after I got here, I had this interest in collecting some measurements off of the CBL pier because it was right there. It was easy to get to, and so much of the work that I had done before I had come here had been looking at these long time series of data that were collected regularly. And I realized that if I had an opportunity to do not whatever I wanted, but a little bit of what I wanted, have a little bit more control right off that pier. And I also had obviously recognized that at CBL, we're sitting in a location where we have one of the longest continuously measured temperature and salinity records anywhere in the ocean. And it was just this golden opportunity. And working with my colleagues, Tom Miller and Laura Harris, we got some money and we were able to, from the National Science Foundation, we were able to re-instrument the pier and keep this time series going. And that's one of the reasons why I'm the one here talking to you right now, is to tell you a little bit about the history of this monitoring that's gone on the CBL pier and what we've learned. And so one thing I will say about this, thank you for being here, because any talk that has the title monitoring in it, I think would put most scientists to sleep, because it's like monitoring, but it's one of these things that doesn't necessarily come off as very exciting, but when we just think about the critical things that we monitor in our everyday lives, whether it be our blood chemistry or our bank accounts, it's one of these boring yet essential things that we do to sort of have an understanding of where we are and where we're going and where we've been. And so maybe many of you are familiar with this curve. This is the carbon dioxide record in the atmosphere at Mauna Loa that Charles Keeling started collecting in the 1950s. And when he started collecting the carbon dioxide measurements to do this, he wasn't thinking about this long-term increase in the climate change that we might associate with it. But sure enough, after reliably collecting quality information day in and day out, we get a record that tells us something absolutely essential about the globe. And so monitoring is this way that we can understand the past, we can understand just natural variability, we can track the success of things that we've hoped to have an impact on, and we maybe will identify things that we weren't even expecting to see, like Keeling did at Mauna Loa. So I'm going to talk about the pier primarily today within the context of CBL's overall monitoring footprint, but there's a lot of other things that CBL has done to do monitoring. We have these Patuxent River cruises that some of you have come to these before, have probably heard about. Some of the colleagues here, Walter Boynton is here, developed something called data flow, where they hooked this a sensor up to the hull pump of a boat, drove around really slowly. And all of a sudden you could map really fine scale patterns of things like oxygen and algal concentrations. And this technology actually went and used by state government to sort of do regular monitoring in the bay. And those of you who have been here before have probably learned about the Calvert Creeks monitoring program that CBL has done in partnership with the county since the 80s. So there's a lot of different ways in which CBL has been involved in monitoring, but I'm going to focus on the pier today. And so I was feeling inadequate about giving this presentation because I realized that I didn't have a super complete history of all the people that have run this pier monitoring program that I'm going to tell you about. And what I've started to piece together is that I think the earliest person outside of maybe Truett's involvement was George Francis Bevan, who, as Carys said, one of our other buildings, our flagship building, is named after. And Bevan, at least I think until around 1940, was managing this program, measuring salinity and temperature off the pier. And it started with salinity and temperature. And in his first paper that he wrote about it, which was published in the early 60s, he made this point: a knowledge of such variations at a given point offers a useful means of relating certain biological and physical phenomena to an accompanying temperature and salinity. So he wanted to just be able to document what the salinity and temperature conditions were, in part because he was a fisheries ecologist, and that was essential for understanding the organisms that he was studying. And that was just the start of it. And now a history has emerged from that. So the foundation of this program is just temperature and salinity measurements taken since 1938, nearly continuously since 1938. New measurements have been added over time, and I'm going to talk about some of those chemical, biological, physical measurements a bit today. New approaches and tools have been brought into the program over time. We have a colleague out there now that has a camera that's taking real-time images of all the microscopic and macroscopic plankton that are swimming around in the bay, in the end of the river. And the sampling that has done, originally every day somebody went out there and made a salinity and temperature measurements. Then I'm not sure exactly what changed, but I think they cut out the weekends. Maybe they realized they had to be a bit more civilized. And now we have modern sensors, so real-time data generation is huge. And so one of our colleagues had put this together. Between 1938 and 2011, there were 1,000 records collected off the pier. Between 2011 and 2017, there were 11,000 records collected off the pier. Yesterday, there were 11,000 records collected off the pier. So the technology that we've used is amazing. And so to demonstrate that, so this is what we have out there right now to measure salinity and temperature. It doesn't really have anything on it, but this will measure one of those properties every 15 minutes. And this will measure about 8 variables at one time. You'll notice the brown here, fouling is one of our biggest issues. We wrap these in copper. It's one of the simplest, not super effective, but kind of effective way to keep things from growing on these sensors. In Bevan's day, the way you measured salinity was that you took a sample of water. I'm not exactly sure if they used a graduated cylinder. But how many of you have brewed beer before? You probably have used something like this before to measure your initial and final gravity. Well, it's the same idea. This is a calibrated bulb. You drop it in your water. You have to squint and you can kind of see what this value is. And then you have a table that, based on the temperature and what you measure here, will tell you what the salinity is. And that's what they did. So it's a lot easier to get samples today than before. So over time of this program, when I was putting this together, I started thinking about all the things that have changed. And I'll come back to that later, but many of you that have come to these seminars before have probably seen these old aerial photos of the island. This is from the 1930s. You know, a fairly unarmored shoreline, among other things, and surrounded by plants growing on the bottom of the river. And this is a recent picture from a friend flying over the island, and you can see we have a completely armored shoreline, more or less. Here's our pier, and you can still see structures on the bottom, but instead of plants, we have oyster cages and we have an active oyster lease out there. And so years after the monitoring program started, you know, we had a lot of things that have happened with regards to environmental advocacy in our country. We had the Clean Air and Water Acts in the 70s. The Chesapeake Bay Program synthesis study happened in 1977 that tried to set the stage for the Chesapeake Bay Program, the restoration program that would follow. 1983 and 1984, Chesapeake Bay Agreement established the federal-state partnership trying to restore the bay. In the Patuxent, and I think Andrew will talk about this, there was a major effort to upgrade wastewater treatment plants for more advanced nutrient removal. That started in the 90s and has continued on since then. The nutrient diet for the Chesapeake Bay was set in 2010. And in 2015 is when we established the most modern version of the program, which is in existence today. Okay. So doing this is really hard. If not only do you have to be sort of devoted enough to be doing it regularly, so it's amazing that it's been going on for 80 years. But you almost never know what you're going to run into when you go out there, both in terms of the conditions and what you find with the sensors that you have out there. So for example, here's one of our sondes that got banged around too much in its housing. It lost its little protective cap. Sensors fell to the bottom of the river and we had to kind of salvage things. This is where we measure how much radiation is coming from the sun. And the birds really like anything, as you know. And so I went to the hardware store and bought some pins and they lasted for about 3 days and we just gave up. It can be quite cold. And this is a housing that we use to try to protect that sonde over there. And this is it just covered in barnacles. And so one of the challenges to doing this is that there's always an excuse to not get out there enough to take care of things because everything will go wrong that can go wrong. So this is just a bit of a snapshot just to show you some pictures about kind of what the modern system looks like. So many of you have probably boated or been around the pier. We added these sensors for how much radiation is coming from the sun, the fraction that the plants can use, and then all the shortwave radiation. And we use this to try to understand, how changes in cloudiness affect productivity. We have an instrument measuring the current velocity going back the pier, which has been interesting because the current velocities at the incoming tide are almost twice as much as they are on the ebb, we discovered. NOAA has a bunch of infrastructure out there, and it turns out that this program has always kind of been matched with the tidal monitoring that's going on out there. And Hongsheng B, our colleague's plankton imaging system that I talked about, is out there. And all of these sensors, not the NOAA stuff, but our other sensors all come into this house here, into this setup here. We have a data logger, some backup batteries, all of the different interfaces that communicate with the different sensors that are out there. And then every 15 minutes, this data logger has a program that tells everything to sample. And then this box communicates all that data back over the Ethernet back here to a computer that sends the data to a cloud-based service on the internet. And then it shows up in our online monitoring system, which I'll show you there. So this is what that system looks like if you've never seen it. Anybody that hasn't seen this, will make sure you get the website tonight, but we have all of our data that we collect out there on a website, and you can come and see what the salinity is, what the water temperature is if you happen to be going out fishing. And then we have other things, like one of our colleagues at Horn Point, Raleigh Hood, and some of his colleagues created a predictor for how likelihood you are to encounter a sea nettle based on the salinity and the temperature of the water. And so you can go out and see how likely that is. Don't hold me to it, but you can do that. And this same tool NOAA has running in near real time, where you could look in anywhere in the bay to see where you might encounter these organisms. So that's another resource that's out there. Okay. How did we get here? Oh, I cut out a slide. Anyway, the next thing I want to do is talk about some of the long-term records that we've collected at the pier. And so the first one is the temperature record. And many of you have probably seen this before. In fact, you've seen some version of it when you came and drove in here today. But just like Keeling, we started recording temperature in the late 30s. And for a long time, nothing really changed. And in fact, the first papers that were published by Bevan and some of the colleagues that he worked with at that time in the 60s really just gave descriptive statistics about what they measured in terms of salinity and temperature. But as more and more people came back to this record, and Dave Secor and one of his technicians looked at this originally and noticed that there was this long-term increase. And the temperature there has gone up by somewhere between 3 and 5 degrees since this record was collected. Now, this isn't Celsius. So we found this record in warming that we've now seen in other data sets that have emerged in the Bay. And it's one of these things that maybe in and of itself hasn't changed management because the management already knew about this. But the Bay program's nutrient diet has been changed to try to account for what the effects might be of this on what the future Bay looks like. And so many of you have probably seen these climate stripes. This is the way that we've tried to illustrate this in a little bit more of an illustrative way. But when I was looking at this and just thinking about back in time, you know, just all the things in the world that have happened while this monitoring program has been in place. It's remarkable to think how different the world was in 1938 and everything that's happened until we got here. And one of those other things that have happened is that we went from being primarily blue to being really red. That's not a political statement, but that's the temperature. So this is something that we have to reckon with, and it's just one of those long-term records we collected up here. Okay, so maybe you've seen the temperature record, but maybe you haven't seen the salinity record. And I don't know that there's too much I can say about this, but this record just really shows a lot of interesting things. So again, we're in 1938 back here. And so for those of you who are around here, the 1960s was a really dry period. And if you look at the salinity levels there, you can see that some of the higher levels we had there, and just the tendency here tended to be high in the 60s. And I think everybody had too much fun in the 60s because in the 70s was just a deluge of rain. And you can see how just low the salinity was for the latter part of that decade. Tropical Storm Agnes, that passing in the early 70s was probably the most remarkable feature of that decade. And maybe one of the other things that's interesting is I'm sure many of you were here in 2018 and 2019 when we had that historic precipitation. The salinity dropped down to about 5 or 6, and it stayed that way for months. And the extreme low wasn't really that remarkable, but the duration of time that it was that low was pretty remarkable. And the grower that has oysters out there on the pier told me he had 25% mortality, 25% of his oysters, I think, did okay, and 50% did nothing over the course of this record. So it's one of these ways in which we can use these data to understand the things that are happening right out there. The one thing that I haven't done any sort of statistics on yet, so don't hold me to this, is that if you look at kind of where the bottom hangs out, the salinity at the bottom kind of hangs around here in the first part of the record, and it seems to be hitting lows more frequently in the latter part of the record. And so to me, this isn't quite all that surprising because if you look at the precipitation records for the Patuxent watershed, they show increasing precipitation over this same time period. So there's a signal of that increasing rain, which is something that's predicted to continue to happen here. But the interesting thing is if you look at salinity records and similar analyses that have been done out in the main stem, they've almost showed the opposite pattern. And so that pattern is associated with sea level rise. But here, at least based on this record, which I haven't analyzed any more than what I'm showing you right now, maybe suggests that the watershed effect is a little bit more important than that remote sea level effect. Which is interesting because this is happening more and more on the island. Maybe most of you have experienced this. You know, it was after a few years, once we were running this program and we were reporting the NOAA water levels on our website, that I realized that we could probably figure out where that water level line was when this road was flooded. And so we had this very scientific process by which I had a handful of people texting me when they saw water on the road when they were coming into work. And we figured out, okay, this is about the line where we're going to see flooding happening on the island. And so now if you're interested, you can go there and get a sense of when you're going to see flooding. And the red line where we have it now is about at the place where you're going to struggle to avoid the water if you're coming down this island. Originally, it was like there was some water on the island. Now it's just there could be any. And this graph looks terrible, but recently we wanted to kind of look at what the recent records looked like relative to this water level on Solomons. In the past, people have shown that the sea level rise is really accelerated here. The record we have out there shows a really strong increase in sea level. But if we look at these thresholds for where water is, where 1 meter relative to mean low is basically there's water clear across the road. This is what it looks like relative to 1980. So if you felt like there's more water on Solomon's Island in recent decades, the data suggests that yes, that you're not imagining that. That's a part of this long-term sea level rise record here. Okay, so the last thing I want to tell you is moving away from sort of the things well, how do I want to say this? Something fundamental that we learned by doing this monitoring. So I'm an ecologist that likes to study oxygen depletion. And one of the measurements we make to understand that is we put a water sample in a bottle and we incubate it at the temperature we collected it at, and we see how fast the oxygen disappears. And it gives us an indication of how much the water is consuming oxygen. And so when we started the new version of this program in 2015, we started an effort where every 2 weeks we went out there and we made that measurement in the surface water. And recently I had a summer student here that was interested in this topic. And so he went back and looked at this almost 10-year record of these measurements that we make. And so what we do here is we take 3 bottles and we fill them with water and we measure the oxygen in them using a relatively simple approach. We put them in the water, hang them off the floating dock out there. For 6 to 24 hours, we have to let it go longer in the winter. And then we measure the oxygen at the end. And it always goes down, sometimes by a little, sometimes by a lot. And so by computing that difference over the time over which we incubate it, we can calculate a rate. And for us ecologists, rates are really important because they're not just a snapshot of what's happening in time. They give us some indication of how things are changing. So let me just give you a little tidbit of the most interesting thing that came out of that. I'll try to not talk about all these time series, but this is that rate of oxygen consumption, we can call it that. And these are every 2 weeks from 2015 out to 2023. So there's a couple things. They get bigger in the summer and smaller in the winter. And we had this really big peak that happened from 2018 to 2019 in the months and maybe the year after all that rain happened. So all that rain brought all these nutrients into the bay, stimulated all this growth of algae, and when they started respiring, they consumed the oxygen. The other thing we saw is this measure of kind of the particulate material that the organisms really like to chew up and consume oxygen, particulate nitrogen. We also found that it was really high at that time. And so these things, we kind of would have expected it. But one of the things that we didn't expect is that this is David, who from the University of Rochester. We measure sort of where we are in the tide every time that we make this measurement. And David noticed that the respiration rates, which are sort of grouped here by tide height, as you got bigger tide, you were in the higher part of the tide, this rate was higher. So it suggested that there's something about when this high tide water is coming in, maybe from the Chesapeake Bay, you're getting more of this organic material, you're getting more of these oxygen rates. And when he discovered this, we remembered that one of the REUs that came, these summer students, about 10 years before him, had gone out and measured respiration every in consecutive 10 days. And so at different points in the tide. And when Joanne, who's now a PhD student at Hopkins, did that, he found this, kind of weak but positive relationship between tide height and respiration rate. And we've got a couple other pieces of information that we've pulled together with us that give us this indication that there's this influence of the Chesapeake, at least in this very lower part of the Patuxent, that's driving, these rates. And so it tells us a little bit of how this pier station is sort of 1 part Chesapeake, maybe 1 part Patuxent. Anyway, so I'll conclude here just to say we've maintained one of these really long monitoring records And these measurements have documented changes in sea level, warming of the bay, and the influence of the bay on the lower Patuxent. We've learned a lot over the past 80 years. We have a lot of new information coming from the modern system, which is allowing us to push out more information to all of you more frequently. And that there's new approaches and tools that are emerging and technologies to even allow us to push things further and further. And I think what you're going to learn about from Andrew and Carys is some of the ways that we're trying to do that. So, Andrew, pass it on to you.
All right, so when I came to CBL 25 years ago, I came to work with a couple of people. Joel Baker and Rob Mason were here at the time, and they were pushing the envelope of organics and metal analysis, looking and working in the Chesapeake Bay. So one of the things that happened, of course, is what we referred to earlier, is the 1970s is when things started to change. We started to actually act on some of the issues that had been identified. We upgraded wastewater facilities, both in the Patuxent River and up in the Potomac River, Blue Plains. And one of the questions that we had is like, how are we doing? Well, we can go out there and we can measure nitrogen, but we've also discovered there are other things that we can measure to give us a good indication of what we're doing. What about other sources of nutrients? Okay, well, you fixed the wastewater treatment plants, or so you think. But what about other sources? Most of us are on septic systems. Well, what about them and what do they contribute? And then what about other chemicals? As we know, there's a lot of other things that we use and they're out there, some historic problems, especially around Baltimore Harbor. And we've dumped a lot of things into the rivers and waterways, which have made its way to the Chesapeake Bay. So what about them? So as I said, I came to work with Joel Baker and Rob Mason. They've been monitoring a number of compounds. It was very challenging. It was very expensive. And we were learning to develop new tools and methods to do a lot of these analysis on the fly. And a lot of this is as we looked at polychlorinated biphenyls and PAHs. In particular, maps of these now exist from some of this work. Maps about metals as well are found from the Bay program, which give you some idea of the distribution of these things around the Bay. Where are the hot spots? Where you can imagine Baltimore, of course, around Washington, D.C., and down in Norfolk area, there are places where we have highly contaminated sites. Most of the sampling has been done what I would call temporally. You go out there and you take one shot, you go look at the sediment, you go measure the water, come back, you do the analysis, and a few years later, you produce a report and you give an indication of what it looks like. Snapshots in time. The continuous monitoring that Jeremy talked about is something that we've struggled with a lot of these compounds because they're expensive to measure and they take a lot of time. During this time period, though, we developed a number of methods to hopefully move this along with some different ideas. And we produced a number of graduate students who've gone on around the world to amazing, successful careers that have come out of this group. And I just want one shout out to Heather Stapleton, who's down at Duke University, and she worked on these flame retardants. And I'll come back to what she is doing now, which is based on some of the things that we've done here. So one of the things we decided early on was we needed integrators that would collect compounds over time. And you can do this a couple of ways. You can make them, or you can use organisms. So we've used organisms a lot. We've used flying oysters. We hang them out. They accumulate compounds over time. We give an idea of what's present and whether or not they're bioavailable at the same time. We've done other technologies. I've done things like this diffusion gradients and thin films. These are like discs. These are things made of things like polyacrylamide. The compound of interest slowly diffuses into that. You know what the diffusion rate is. You can back out a concentration. And that's what actually Heather has actually done. And she uses a silicone bracelet. She puts that on babies. She puts them in cars or when they're sleeping at night. And they accumulate flame retardants so they can get some form of exposure. So she learned some of the stuff from doing this water monitoring that we've done. So we've done this quite successfully. Carys and I did this work in the Gulf of Mexico with oysters and looking at things accumulating, growing on structures. We've used these diffusion gradients in thin films. I've done them to look at mercury. We've done them to look at sulfide. So these things can work. The question though is again, they're somewhat limited in scope. How long does your oyster live? You know, you have to sequentially sample them over time. So you can only do it for so long. And we have difficulty challenging our funders to provide us support to do this kind of research. You can't just monitor this stuff for the sake of monitoring when it costs hundreds of thousands of dollars. You have to have a reason. So that's one of the things that we have to sort of weave this stuff into some of the things that we are already doing. And I'm going to give you one example of that here. So back in the 1990s, we were looking at mercury deposition. And we finally started understanding where it was coming from, and we started turning some of these things off. So we started removing waste incinerators. We started putting activated carbon injection on coal-fired power plants. So back somewhere around 2014 or so, 2012, we started actually having a good response. We also had put on sulfur scrubbers that also helped remove some of the mercury. So what we were interested in was, what is this impact of these sort of remediation technologies on mercury deposition? One of the problems that we have globally was mercury concentrations in fish were high, such that we couldn't eat fish from many systems. And these are pristine systems too. So mercury was going up into the atmosphere, flowing around and dropping out into our water bodies. So what we wanted to know was how effective were these? And what you've got over here is this is total mercury concentration and precipitation, and it's going down over time. And we've got mercury in dry deposition measured by looking at leaf litter. And then this is the Savage Reservoir, and this is fish. This is young of the year fish. So we go out every year, we sample the fish, we measure the mercury concentrations. That fish is recording the mercury that's accumulated just from 1 year. So it's an indicator. So this is where we're monitoring. And sure enough, we see that mercury concentrations are going down. But then in Deep Creek Lake, we didn't see that. We saw something else. Mercury concentrations were going up. So we were monitoring for one thing, but now we've learned something about the Deep Creek system that is something that managers need to know about. Mercury concentrations in these fish are going up, they're not going down. So there's a lot of things going on in the watershed. There's urbanization. Deep Creek Lake has seen a lot of development. There's a lot of sedimentation in that system, erosion from the development. Water level changes. The lake is a reservoir. The water is drawn down every winter so that snow melt comes in, accumulates, fills back up. This reservoir effect is something that I did my PhD work on, where that every time you create a hydroelectric reservoir, you get really high mercury concentrations in fish because the mercury that's stored in the plant matter, as that plant matter decomposes, the mercury gets methylated and it gets accumulated into the fish. Food web changes. This is a managed system. Managed meaning we've introduced so many different fish species into this lake that now it's really, we don't really know what the food web structure looks like at all. So it's probably changing as well. So the longer the food web, the more organic contaminant or methylmercury you accumulate. So the concentrations get higher. And so we're starting to try to figure out, well, what in the world is going on here? And the stuff that came off the instrument last night is up here. So mercury concentrations are continuing to go up. So now we have to figure out what is the source of this and what can we do about it. So now we can respond because we actually have the data. Contaminants of emerging concern. California suggests there's about 2,000 new chemicals introduced to the U.S. economy every year. It's kind of hard for us to keep up. They are grouped innocuously: personal care products, plant care products, herbicides, pesticides, pharmaceuticals, all the kinds of drugs that we use, and then food additives. I was like this: cellophane keeps things clean. You know, all these things are useful, but we have to understand the full life cycle of the chemical. You know, what it's used for, where it ends up. So that's what we've started to do. And we're using the Patuxent River, as we've talked about, as a sort of a case study to try to understand what are the sources of these contaminants in a system that looks fairly pristine. Down here, you know, it's highly forested now. We've reclaimed a lot of the agricultural land and we've planted trees. There's a lot of urbanization in the upper part of the watershed. And then when you get further up here, you get a reasonable amount of agriculture still. So you've got a lot of complex sources in the watershed, bringing nutrients down here and other chemicals. We have power plants over here where we have metals and other organic contaminants released for a while. And then we have our harbors where we dump a lot of things as well that are coming off boats. You know, Jeremy referred to copper. We coat all our hulls with copper, and that's not a good thing. It's good for your boat. It's not good for the environment because it's designed to slough off. So we got a lot of copper. Commercial use, residential land use, and of course, this is history. There's a history of agriculture, so there's some legacy here as well. And so we had this vision that we needed to up our game. We needed to get the technology to be able to measure the presence of these compounds in the environment, and that's not easy to do. These instruments are fairly expensive. The methods to do the analysis are complex, and it takes a while to get this thing up and running. So what we have created here is the ACES Center. We have 3 triple quad mass spectrometers where we can measure a lot of these organic contaminants. And they go along with our ICP-MSs, which we can now measure metals, so we can have the whole shebang together to actually begin to tackle this problem. So as I say, we have this sort of vision. We have all these different sources of different types of things coming into the watershed, and it gets amazing, right? You've got pharmaceutical drugs coming from livestock. You've got farming, you've got pesticides and nutrients and herbicides. We've got some light industry. We've got road drainage, which I'll talk about momentarily. We've got septic systems, and then we've got our wastewater effluents. And then, of course, all the things which come from that are pharmaceuticals and things coming out of these things. Algal toxins, another thing that's, of course, of interest in Chesapeake Bay. And then we have to be able to quantify them all. And this is where we're working on right now, is getting up our game to be able to measure many of these compounds with the idea to try to get an environmental impact. Just what are the important ones? We don't even know what the important ones are yet. We know there's a lot of them out there. And then what kind of guidance can we have? The fluoridated compounds. So this is one of the first things we started tackling. I'm sure everyone's heard of PFAS, these forever chemicals from our Teflon and things, and from foams and things like that from fire, which is one of the big issues on a local scale. So anyway, what we did was of our Patuxent cruises, so in 2024, we collected samples and we actually analyzed them just to get an idea of what it looks like. So this is coming down the river, 301 Bridge, West Branch, Route 4 Bridge, you cross it a lot. And then station 1, 2, 3, and 4 as you come down the river, station 4 being just out here from outside the lab. And what you see up at West Branch here, where the wastewater treatment plant is, you see high concentrations of PFAS that goes right through the wastewater treatment. And then, and if you compare July, where we had a large rain event, compared to October, you see lower concentrations. And what this is basically showing is a dilution. You come down the river, water coming in from other sources, you've got mixing of some salt water in there, so we're just seeing basically dilution, with the sources being upstream. We also started looking at some of these other compounds, pharmaceuticals and sweeteners and tire compounds, again, to just get an idea of what it looks like. And this is what we've found so far. What you see is these are drugs. Sucralose is the one thing we know, that's artificial sweeteners. These are what we call conservative tracers. So basically they're showing that same dilution as you come down the river from the wastewater treatment plant down to solvents. And then what you see over here is the conservative tracers. This is different cruise dates. And the conservative guys don't really change very much. Labile ones, like caffeine, do change, and they give you some indication of what's going on. And this is West Branch, and this is where there's a large wastewater treatment plant. And on that particular day, we had a large rain event, and that wastewater treatment plant was not working very well, and things were coming out. So this gives you some indication of your performance of your wastewater treatment plants. So we could actually see the caffeine come out into the river much higher than it was on other dates. So we have an indication of source. So then you would probably associate a large nitrogen pulse at that point in time and so on, right? And then the last thing I want to talk about is something really new and really interesting to me. This particular compound, 6-PPDQ, is a compound that goes in tires. It became into the news recently because it was killing coho salmon. And this is a very interesting compound because this is acute toxicity. So what they noticed was that when the salmon was swimming upstream to spawn, and this is in Washington, suddenly they would see a bunch of dead salmon when there was a rain event. And they were like, what the world's going on? Like, what compound kills basically instantly these fish? So it took them a decade to sort this out because they had really no clues. And what they found out was this particular compound is a breakdown product of 6-PPD, which is something that goes in your tires. So this compound was coming out into the environment, sitting on the roads and being washed off during a rain event. And when that went into the river, basically it diffused into the gills of the fish and basically immobilized them. And they basically dead within hours. So we wanted to know whether we could see this in our rivers, because while the coho salmon is the only thing that's been acutely killed, there is definitely a toxicity to other types of fish that they started to look at. But now we have the ability, in the last couple of years, we know what we're looking for. And this other compound here is also a tire compound. Tires are rubber. No, they're really amazing conglomerates of chemical compounds. So anyway, we decided to look for this, and this is Route 4 bridge, and we've measured it on 3 different dates. And then this is this rain event that we measured before, where we saw the release from the wastewater treatment plant. So we actually saw a spike in the river during that time period. And then Andrew went out to the Solomon's Bridge here, and what you see here is there's these drains along the bridge all the way across, and they drop down into the parking lots and all the way across the river. With my sophisticated sampling device here, I collected the water coming in, and you can see it's black. It's pretty nasty what comes off that bridge. Anyway, the concentrations that we measured in here are many orders of magnitude above what you see in the river. So there's dilution when it hits the river, of course. And then, of course, this is the toxic level for the coho salmon. And it's many orders of magnitude difference here. So it's screaming high what comes off. And this is quite interesting and alarming because we don't really know what happens when our fish are swimming up and down these rivers and what impacts that might have. So this is something that we're quite interested in, and will be something we're working on in the next few years. Carys.
Okay. Well, so I'm just going to end the presentation here by talking about something a little different. As I said, we do the monitoring for a number of different reasons. And one of them is actually to look at what are some of the potential compounds that have, toxicity to organisms and potentially to ourselves. We provide advice to legislators and managers on what they should be looking for as emerging contaminants of concern. So one that we've been working on for the last 10 years, and I would like to point out that we focus a lot here on our CBL, our peer monitoring and our local monitoring, but our scientists here go global with the same tools and techniques and approaches all the way from the Arctic to the reefs. And so this is just one example of a global reach that we're doing. We were asked to look at, it was raised 10 years ago, UV, sunscreens are killing corals. I'm sure you all heard that. So we were asked to, well, is that true? And to do that, you have to do these approaches in terms of you've got to know what's in the water, you've got to know what the toxicity is. So this is what's called an environmental risk assessment. So one take-home point is just because you detect something in the water does not mean it causes harm. The concentration is important, but also it has to get into an organism. So just detecting something in the water doesn't necessarily mean harm. So we need 2 data sets to start looking at harm: ecological risk assessments in terms of exposure. So you need to know the concentration that's in the environment, what level are you potentially being exposed to? And then you need to do what's called a hazard assessment. So you take organisms or model it and figure out what the toxicity is. And then you look at these 2 numerical values. It's a little bit more complicated than that, but that tells you about the risk. So is that contaminant a risk to the environment or is it not? This is how you can prioritize contaminants of concern. So this requires a lot of studies. It'll estimate the concentration of a chemical associated with harm. It can identify the most toxic chemical, and it can help guide management regulatory decisions. So if you have no exposure, you have no risk. If you have no effect, you have no risk. But something I'm going to go on my soapbox here, like detection does not mean harm. You'll see in all of the articles, we've detected this here, we've detected this here. Great red flags, and it's how we need to follow up and look at potential issues. But just because we see something in the environment, we need to do a little bit more in terms of measurements, figuring it out, and then what the toxicity is of it. So I tell you, go back to our 14th century with Paracelsus. And because you hear now, toxic chemical, safe chemical. Well, I just wanted to point out that every chemical is toxic. Go back to the father of toxicity, Paracelsus. It's the concentration and time that is critical. Everything is a poison at a certain dose. So the question is, at what does the organism get exposed at that concentration of the toxic chemical? How is it exposed? Exposure routes are key. Is it eating it? Is it being absorbed across its gills? So exposure routes is key. So this is where we came in. It's just one slide. I just wanted to give you an example of a study we're working on. I love coral reefs, and I really like working on those, not because it's in a tropical environment, or there might be something to say for that, but they're a very sensitive, just wonderful ecosystem. And so we were asked to address the question: do UV filters that are in sunscreens, do they kill corals? And so to do that risk assessment, we have to know the chemical's toxicity. So we've been doing with partners at Nova Southeastern toxicity experiments. And we also need to know the environmental concentration. So we, Andrew and Michael Gonzia and myself, have gone to, again, terrible job to focus on coral reefs. We've gone to Hawaii and Florida to determine the spatial concentrations of these things. And so this is what's also important is so if you're thinking about a coral or the toxicity of the coral, corals are down here, they're in the benthic. What's the concentration of the chemical here? But corals also put out larvae. And so if you think of sunscreens, you can think you might have a slick up here. This is the micro layer. That's your concentration there. Normally in the environment, what we do is we'll measure here in the surface layers. So you can see we wanted to know, well, what's the difference between the micro layer, the surface layer, the deep, to have a better assessment on the impact on corals. And then also, as Andrew spoke to earlier, temporal is important. So, the hypothesis is this is coming from people, right? Are people in the water 24/7? No, well, maybe some are, but a lot are not. They start peaking in the afternoon. And so it's really important to know from a daily perspective. Obviously, you're going to get different concentrations in the winter versus the summer, and over the time of the day. Does it change? So this is down in Florida. So again, you can see 2 p.m. more people in the water. 8 p.m. they're gone pretty quick. And this is Michael Gonzia's fantastic device that he built. It's a rotating drum that collects the sea surface microlayer. And so we can look at the concentration specifically in the microlayer. Got a lot of funny looks for this floating device there, but it's a microlayer sampler. So this is the one data slide I'm going to show you. This is from sampling we did last summer at Fort Lauderdale. We actually went out 2 times. We went at spring break thinking there'll be loads of people. There wasn't. We have a great ability to go when the weather's really bad. So it was really cold, and so there wasn't as many people, but we went back on, we're determined. We went back on Memorial Day, and then there was loads of people. So just what we were looking at is, well, is it coming from people? And how does it change over the day, and how does it change distance from the shore? So here's your beach. T1 here, this is your bathing zone. We're going along, collecting samples about this high with all the people looking at us like, what are you doing? And then Michael Gonzia, because he's a lot taller than me, he was out here. It was about 30 meters out, but he was up to here and also doing the same thing. So we could see what the dilution was as we moved away from the beach. So the take-home message here, So this is the blue is right on the near shore. You can see early in the morning, oh, it's 9 o'clock. There's really very low concentrations, and as more and more people are coming on, you get increased concentrations. When people start leaving, it goes down again to back to base. So really fit. It looked like we made this data up. It completely fits our hypothesis. It was awesome. And then the other thing is that just slightly further away from the beach, same sort of trend, but much lower concentrations. So again, it was, showing the real importance of these really detailed monitoring. And now that we have this data, we now can build this into models that can predict what these concentrations might be at other locations. So that was all I had to say. I just wanted to summarize our CBL monitoring program. We have a 100-year dedication to water quality monitoring. It's provided a lot of insights on the long-term changes, implications, not just for the health of the bay, but impacts to our economy, our resources, our way of life, including issues relating to sea level, the warming of the bay, all the things that you've just been presented. The modern peer system brings real-time information to predict potential issues. Are you going to go out swimming today? No, jellyfish, not going to go. And coastal flooding, don't come onto the island if you can't get off. There's two ways on, there's one way off. So, I always keep an eye on that wonderful Patuxent Centennial site. We also have new approaches and tools, we're expanding our knowledge of basic science, the health of the bay, the identification of emerging contaminants of concern, and we'll be addressing these for the next 100 years and our mission to protect our natural resources. Other CBL studies also do a lot of this water quality monitoring, addressing all sorts of global issues, changing ecosystems in the Arctic, pollution impacts on coral reefs, changing biogeochemical cycles, and also issues related to climate change. So with that, thank you so much for your attention. Thank you again for being here. We'll take questions.